Hello, everyone. This is Group 1 presenting digital transmission in free space through a high-powered laser. Our mentors being Dr. Wei and Dr. Carr, our committee being Dr. Sahawin and Dr. Maddox and Dr. Eikenberry.
This is our optical diagram. I will only be going over the transmitter portion of it, which covers the infrared, the red laser beam combiner, the beam expander, the culmination lens, and then the alignment mirrors. The infrared, as you can see, is at 980 nanometers at 600 or 60 milliwatts at higher power. Red lasers 636 nanometers at 5 milliwatts of power. Our beam combiner, then we have our beam expander of 36.1 millimeters and our culmination lens of 50 millimeters. Then onto our alignment. This is the optical layout schematic shown in 3D modeling CAD and what we're planning to print out. Next is it actually being assembled, and you can see our infrared laser, our beam combiner, our red laser, then our beam expander, our culmination lens, our adjustment mirror, and then our output. This is us, or me, testing the system first to make sure for our long distance test that the beam size is what we need it to be. You can see it going through the beam combiner, our beam expander, culmination lens, see there, and then through our adjustment mirror, and then to our output, where you can see it's going and gradually getting bigger. And then for a distance about like 10 to 15 feet, you can see that our beam size is about 1.5 inches. We went later to adjust that. And this is our beam size at longer distance, 60 feet. We did about tested the beam size at about halfway point. This is the IR at a halfway point. You can see us standing there, walking through. The halfway point about 35 feet. You can see on the IR viewer card right there, about half of it is on the screen. And that's about 1/2 inch to 3/4 of an inch in size, so we need to further adjust that. And this is our version we had before our final demo at our Creole Showcase project. You can see the version we have showing the character we are transmitting in a loop, the binary code for the character, the modulation board, and the IR laser, transmission, the laser in a loop. And we go through our beam splitter, culmination lens, beam expander, mirror, receiving end, and then receiving end, our photodiode, focusing lens. And then you can see at there we have the receiving signal, our high and low signals, our max signal we've gotten through the loop, and the amount of bits that it is read throughout the entire loop.
For the photonics demo, we measured the power of the focused laser at different distances, and we try to keep the laser power above 5%, which is our minimum laser power achieved at a certain distance. And we measured the laser power at 10 distances and measured up to 100 feet. And these are our results. And the highlighted values are in the demo videos. And then for the specification calculations, the average focused laser power is 10.51 milliwatts with an average of 8.76% of power lost from 120 milliwatts. And then the average amount of photocurrent generated is 6.83 milliamps, and this is expected. And heads up on the videos, the second demo video I misspoke. It's supposed to be demo 2 and not 3.
This is the start of the hardware design. This slide shows an overview of our hardware pipeline. It starts with a microcontroller that converts written text from the laptop to binary data that will be used to toggle the laser in a subsequent manner so that zeros will represent when it is off and ones will represent when it is on. The laser beam then travels through an optical path composed of lenses and mirrors for beam shaping and collimation. At the receiving end, a photodiode captures the signal and the output current is converted to voltage using a transimpedance amplifier. Using the microcontroller's built-in analog-to-digital converter, the signal is then processed by the microcontroller and its output is then sent to the LCD to be displayed. Using Fusion 360, we developed a detailed 3D CAD model of the physical system, including the PCB container, condensed component layout, and light optical mounting. Two additional views are zoomed in to show how components like the PCB and photodiode are positioned for alignment. Creating this model helped guide physical prototyping by verifying mechanical fit, optical paths, and wire routing in advance. In this video, you can see our system in action during a test run. The laser transmitter sends binary encoded characters through free space, which are then picked up by the photodiode on the receiver side. Initially, we ran into major timing issues when using an ATmega microcontroller to receive the signal because it couldn't synchronize properly with the MSP430 transmitter, leading to decoding errors. Switching to the MSP430 on the receiver side greatly improved consistency and helped us troubleshoot and verify that each subsystem, from the laser modulation to the transimpedance amplifier and LCD output, was working as intended. This prototyping stage was key in validating our hardware choices and refining our signal detection pipeline. This clip highlights the receiver side PCB we designed for our optical communication system. You can see the photodiode mounted near the top edge, positioned to capture the incoming laser pulses. The signal then travels through our custom transimpedance amplifier, which converts the light-induced current into a readable voltage. From there, it's fed into the MSP430's microcontroller, which decodes the digital signal and sends it to the LCD. We also included a 3.3 volt and 5 volt regulator for subsystem power isolation, as well as header pins for programming and debugging. Prototyping on this custom board let us validate our design choices in a real-world environment and ensure signal integrity from our optical input all the way to visual display.
Hello, my name is Monica. This is the test demo, which is the transmitter and the receiver. During our test demo phase, we tested countless times with sending out words like SOS and hello. We would always get a possible 1 or 2 characters correct. We had to move forward with a different plan with the same goal of transmitting over a signal using binary, so that the receiver is able to translate each bit and let the user know what was sent out. As you can see, the transmitter is on the left side and the receiver is on the right side, as well as the photodiodes in the middle and the laser as well. On this side, as you can see, is the transmitter. During our development, we ran into several key issues that required some troubleshooting and redesign. First, we had resynchronization issues between the transmitter and the receiver. The binary data being sent via the laser wasn't aligning properly on the receiving end, which led to miscommunication and completely incorrect characters being displayed on the LCD. To address this, we are now implementing a start and stop signal around each byte. This helps the receiver detect the beginning and end of each character and resynchronize if it ever gets out of phase. Another issue was the UR communication using putty. The user input wasn't showing up correctly on the LCD or sometimes wasn't capturing at all. After checking things like baud rate, wiring, and software buffers, we decided to hard code text messages for the purposes of the demo while we continue debugging the UR configurations, verifying the COM port settings. And lastly, we noticed that the laser and binary display timing wasn't completely consistent enough for reliable decoding. Some bits were either too fast to register or not aligning with the LCD updates. To fix this, we fine-tuned the delay timing between each bit and added basic validation routines to help the receiver stay in sync. With the blinking signals, all of these adjustments brought us closer to stable integration systems for all final designs. This is the receiver. It had some issues with it also not being in sync. It also was sensitive to noise and environment interference. It also didn't know how to signal or even recognize when the lasers were starting. The goal with this was to get it in sync with the transmitter and get it to know the delays, as well as we got it to reset with the first 3 blinks, which helped it tremendously. All right, thank you for watching. This is digital transmission in free space through a high power laser. This is group 1. Thank you.